Hello, welcome back. This is practice problem number 2 from week 10 of Intro to Electrical and Computer Engineering at UTEP. I'm Dr. Roberts. And this is just part of a bunch of practice problems I thought it'd be helpful for you to see and see them work live. Where if you joined the previous video, we were asked in problem 1 to find the equivalent resistance and determine V sub A for this equation right here with 3 resistors. Well, now in practice problem 2, we're going to do the same thing, but for a slightly different equation or circuit, right? Boop, boop, boop. Doing this live so you get my verbal typo there. Right, so if here's the circuit we're going to look at this time. Right, this is R1, R2, and C1, and part A is going to ask us is to find equivalent impedance, ZQ, in shorthand notation, and B, determine V sub A in shorthand notation, right? Where again, this is V sub A here, right? So find the equivalent impedance now, and that. Where again, if we look at these circuits, what you'll see is these look almost identical, where only R3 has now been replaced with a capacitor. Well, let's think about this for a minute. Now, what did we learn in class is, well, hey, if we see a capacitor, we should use phasors to move our circuit from the time domain to the frequency domain, right? And if you recall, a capacitor in the time domain goes to the frequency domain is 1 over j omega c, and a resistor in the time domain stays a resistor in the frequency domain. So if we do that, we can then say, hey, okay, well, let's convert this into the phasor domain, right? Phasor domain. And we can now redraw our circuit so we can see what we've done. So plus minus here, we have Vn, we have R1, and now I'm going to actually, this is R2, and now that I've converted the capacitor phasor domain, I'm just going to treat this like a resistor. It's a complex resistor, just to remind me, where this now has the value of 1 over j omega C1. Right, so now we treat this and we use all of our stuff. Well, now if you look at this problem, and this is V sub A again, right? This is the exact same problem we just worked in problem 1, but R3 now has this value. So we're going to follow along and do the exact same process there from problem 1, right? So if we want to now find the equivalent impedance, right? Now we call it impedance, not resistance now, because we're in the phasor domain, right? Which is just complex resistance. So now we can look, right? So these two are in parallel, so we can redraw. If we do that, we get lots of practice. This is still R1. Here, and now this is going to be equal to R2 parallel with the quantity 1 over j omega C1. And now we can see, and this is again VA, and these are in series, so now we can redraw it again and combine the two in series. And if we do that, we get a single complex resistor here, Z equivalent, and that's going to be equal to R1 plus R2 parallel 1 over j omega C1. Right, so here is our answer for part A. Right, just like before. Now part B asks us to determine V sub A, right? So, well, again, if we look, the simplest place for V sub A is right here. And just like in practice problem 1, we now have two resistors in series, so we can use a voltage divider, right? So we can say, oh, okay, we know again that V sub I is equal to Vn times, and we can write this in impedance. So the impedance you're measuring across over the equivalent impedance, right? Just like resistance, we just replace R with Z here. Same thing holds true, right? Same rules. So we know Vn, we know the equivalent impedance, and now what's the impedance we're measuring across? Well, again, if we look at VA, it is measuring with respect to ground, so it is measuring across these two elements in parallel. So Z sub I is going to be this value. So if we do that, we can write that, oh, V sub A is equal to Vn times, on top is going to be then R2 parallel 1 over J omega C1, and the bottom is the equivalent, which is going to be R1 plus R2 parallel 1 over J omega C1. So there's part B. And if we now compare this to the previous results we got, right, you can see if you look, they're exactly the same, right? Where, as we said, R3 was just replaced with 1 over J omega C1, and you see the equation's exactly the same, where the only difference is the resistor of R3 just becomes 1 over J omega C1 when that component replaced. But everything else is exactly the same, which is pretty cool. So that concludes practice problem 2, and I will see you in practice problem 3.